So basically, what I have in mind when I say computing with FPGAs is to use FPGAs to do some computations that you would generally do on microprocessors, and to explore what the potential is of this technology to do such computations. So in order to get started, first a couple of points on why this could be a good idea, or why we would like to do these kind of things. And what I'm claiming here is basically that you could have many orders of magnitude improvement in performance and in power consumption when using FPGAs as compared to implementing a particular function on a microprocessor. And I'll show some examples of these kind of applications that we already have for FPGAs. One neat thing about FPGAs is that we have much more degrees of freedom than we have on microprocessors. Also a little bit a scary thing because we really don't know exactly how to deal with all these degrees of freedom, how to handle all the flexibility that we have on this new technology. An advantage of using them is that you can just go into a store and buy some. So instead of proposing a new architecture that is actually doing something very well, and then having to persuade all of the world that this is the next architecture that they should be using, here you can just go into a store, buy these parts, and try to see what you can do with them to compete with general purpose processors in this case. Further advantage of microprocessors is the of FPGAs is their regular structure. So you have a structure that is somewhere between memory and microprocessors. It is more regular than microprocessors, less regular than memory. And ideally, it should be possible to scale this technology much larger. And many people have made this point. There was a talk here actually a couple months ago by Nick Trudenix talking about various parts of these aspects. Disadvantages, offhand, the first thing that you see when using FPGAs is that the latency is going to be slower. So you're running at roughly 5 times less clock frequency. And taking this particular circuit and putting it on an FPGA, you'll also realize that it's about 10 times larger. The ballpark figure is that FPGAs today would use about 80% of their area to allow all the flexible interconnect that they provide. And this is basically wasted area. So if you have a circuit that you put in there, 80% goes for the flexibility that you get with the device. So if we look at the disadvantages further, we see also we have many years of compiler development for microprocessors and programming methodologies and ways of actually dealing with these devices, whereas FPGAs really are just targeted at this point by synthesis tools that are coming from a different field, from implementing chips, and just apply it to FPGAs and you get the circuit in there. It's really not a programming environment. What you have is a design environment that will get you a circuit that works perfectly, but it will take you a long time to get there. So if we look at the summary of all these technologies, we see the availability is very well for the processors, DSPs, and FPGAs. On the ASIC, if you have a fixed function, either the ASIC exists or it doesn't exist. So it depends on what you want to do. Sometimes you get lucky and there is an ASIC that does exactly what you want. Sometimes you have to design it yourself, which is not very useful if you are in a programming environment where you really want to get some task done quickly. Scalability on the ASIC again depends, because depending on what it is that you're implementing. Processors and DSPs present significant challenges. If you have a new technology, you have significantly more area. You have to throw a lot of engineers onto the problem, and they have to try to decide what to do with this added area, how to scale the previous microprocessor onto this larger area that you have now. Again, the degrees of freedom that we had before, FPGAs have a lot at the cost, of course, that we saw before. And the performance and power advantage that you might have theoretically lies between the microprocessor and the ASIC. So you expect that you would have the performance somewhere between a customized ASIC and the microprocessor at the cost of the flexible interconnect. So when I talk about computing with FPGAs, the thing that I have in mind in general is a system where there is a microprocessor that runs most of the code, and there is an FPGA that has some kind of optimization to execute the part of the code that is running most frequently, and that is tied in somehow into the memory system. And I'm not going to get into how you can put these things together. There are many different ways of combining processors, FPGAs, and memory, and lots of people looking into these issues. But yeah, that's not what I'm interested in here. So there are two basic parts of this talk. First, I'll show a couple of performance results and talk a little bit about how people achieve these types of performance, and why there is a benefit of implementing these algorithms on an FPGA. And the second part is talking about how we can get what we've learned from implementing applications to design a programming methodology, so that anybody could just sit down, write a little program, and target FPGAs and get the same kind of performance that we get when we sit down a hardware designer and let him work for a year and figure out the details of a particular application. So here are some of the examples that I had in mind when I said before that we have up to 100 times the performance. And people started in the beginning doing the obvious thing, taking signal processing algorithms, putting them on an FPGA, and showing that for many signal processing algorithms you can actually perform quite well compared to microprocessors. The reason why they're not currently switching everything from microprocessors to FPGAs is simply there is a cost problem, and you can't really get the same cost benefits that you have for a microprocessor. But from the technology itself, there are much more signal processing applications that could run on FPGA than they're currently being run on FPGAs. The same goes for most applications where you have a lot of data that you need to process and simply stream it through an architecture. So if you have this model, you have a lot of data, there is a little algorithm that has to modify this data. It's relatively straightforward to simply stream this data through the FPGA and get very high throughput. This way you also get around the latency problem that I talked about before, where you actually run at 5 times slower clock frequencies. So if you have basically pipelining, you can get around that problem for many applications. Other applications people have tried in earlier FPGA computing projects is to look at encryption, scientific computing, various applications there. One interesting one is an RSA speed record. Basically, the fastest implementation of RSA encryption was done by Mark Shand in '94 and was being run on FPGAs. So using the flexibility that you have on FPGAs actually for that particular point in time created the fastest implementation. So this just shows that there is a way to get around the 5 times longer latency that you have on an FPGA. And the question really arises how you can generalize this thing to all problems, so you don't have to hire Mark Shand to do all your designs, or somebody who is equivalently clever with his designs. And
he is clever.
Yeah. So another interesting project was looking at graphics, and we had a student at Imperial College who implemented OpenGL, or basically the open equivalent, which is a Mesa library, and was running Quake basically accelerated with FPGAs. And again, it took significant design effort, but that's again one way of using FPGAs, simply taking a library, implementing the library functions, then having a general programming interface that uses this library, that doesn't know about FPGAs, and just utilizes the acceleration that you get from implementing this library. Two others interesting applications that we were looking at were trying to look at basically two problems. One is where you have applications that are memory bound. They're limited by the access to memory or the bandwidth to memory. And the question is, can we do something about these type of applications? And two interesting examples here. One is to solve Boolean satisfiability. You can actually implement the Boolean satisfiability problem on FPGAs and get very large speedups there. Some more details on the following slides. And another way of looking at the memory latency problem, where you have to, let's say, follow particular pointer, is a new way to implement data structures and algorithms together as a hardware structure on an FPGA. And this way you don't actually need to go through pointers and go follow each pointer, have the data in your memory in the type of structures that you have in a microprocessor. So there are some examples following here. There's some more detail on the satisfiability that I was talking about. Basically, satisfiability, you take a Boolean equation and you're trying to find an assignment to the input variables that will make this equation true. So what you can do is a brute force search where all you need to do is evaluate the actual equation that you have many times over until you find a possible solution. And using an FPGA, you can take the equation that you want to satisfy, put it down into the FPGA, and simply evaluate it very quickly, because now it's just a circuit in your FPGA. So you have an instance-specific way to configure these FPGAs at runtime. Whenever you get the data from the user, you simply create the circuit, put it in the FPGA, and evaluate it as part of your execution. And the main drawback here that we've encountered is that you can do the brute force search, but still you have decades of research that people have done in order to solve particular Boolean satisfiability problems. And these type of optimizations that they have come up with would have to be adapted to this new way of solving the problem. So it's very hard to compete with these optimized algorithms that you have there. Nevertheless, for a couple of benchmarks that we've looked at, we've managed to outperform microprocessors running the current state-of-the-art in Boolean satisfiability solving. Basically, a tool that is called GRASP that solves Boolean satisfiability. And you can see the 5 benchmarks that I show here. The first one, hole 6, you have a left bar that says software and the right one that has the hardware. Software is the time it takes for GRASP to solve the problem, and hardware is basically the time it takes to solve the problem on an FPGA. The light blue or light gray, depending on your monitor kind of color on the right for hardware, is the time it takes to generate the circuit, and the black part is the time it takes to actually run the circuit. So you can see on the first 3 benchmarks, there is no time to run the circuit, because compared to the time it takes to generate the FPGA circuit, it is really negligible. Once we start to see some speed up, you have a little black graph, black piece of this on top there. And so basically for the last 2 benchmarks, hole 9 and hole 10, you start getting speed ups, where for hole 10, which is the largest one that we put on the FPGA, we got the speed up of 100 times. So the main problem is all these benchmarks that we've used here are really toy problems, and the goal of this research is to try to expand this now to real problems and use it in real software. But this is just to show that there is a huge potential for these kind of things. I was talking about data structures and implementing data structures and algorithms on an FPGA. So we want to avoid the memory wall and the bottleneck that we have in the memory. And one way to do that is to implement the data structure and the algorithm that we want to run over this data structure in the FPGA. And one standard architecture that probably most of you are familiar with is a content addressable memory. And what that really is a data structure with a search algorithm. And you can search the data that is in there relatively quickly. You can add values and delete values relatively quickly. And you don't have to think of the actual data structure and traversing the data structure in order to do this computation. So you can take this type of architecture and put it on an FPGA And whenever somebody needs, let's say, a data structure where you need to search something, you simply implement it as a call to that particular data structure. And there is a similar, or basically a way to encapsulate data structures and their algorithms, which was worked on in C++, called the standard template library, where you simply say what kind of data structure you want, and the library provides you with the right features that you want for that. And you could imagine implementing part of these as specific hardware structures that deal with these data structures. Another newer architecture that shows a different data structure and a different algorithm is, let's say we want to have a graph and we want to solve the reachability problem on that graph. Usually you need to implement the graph as pointers, and you follow the pointers and you figure out if you can go through this entire graph to go from node 1 to the second node. And here is an array-like structure that takes the adjacency matrix that I have on the left, and you can see for each one in the adjacency matrix there is a corresponding OR gate in the architecture on the other side. So it's a very straightforward mapping. Now, adding or deleting nodes or connections between nodes is a simple modification of the structure on the right. And solving the reachability problem is a trivial problem now, because all you need to do is to set the inputs of the particular wires, basically set the wires of the nodes that you want to check and see if the destination nodes can be reached. So let's say, for example, you want to go from node V0 to node V3. You can start at the upper line on top here. So you have here, you start at the top line on this graph, and you can follow the OR gates to see if there is a path to go through all the way to V3. And if you take a close look, you can see that there is a path going through a couple of OR gates and telling you that V3 is reachable from V0. And the delay for this operation is really just a couple of gates through the array. The speed up that was obtained here is in the range of 10 to 1,000 times. And the main bottleneck here is really the size of circuit that you can put in an FPGA and the size of data structure that you can therefore put in there. So after you exceed the size of the FPGA, the problem requires some tiling and partitioning of the initial problem, and that then reduces a little bit the potential benefit that you have. Another example here is encryption. A couple of years ago, I was interested in seeing if there is a benefit of implementing an algorithm on an FPGA compared to a microprocessor in terms of power. So I ran this little example, implemented the encryption, tried to run it on an as low clock frequency as possible, and compared it to the most optimistic performance that I could imagine a microprocessor could ever get. I was looking at two architectures here, the Texas Instruments and the digital strong arm, and basically figured out that we could get 5 to 10 times better performance over power, or power delay product, any way you want to look at that. Now the question arises here, how do we achieve this type of power advantage? Where does it come from? If you look at the architecture that I used, simply taking the data flow graph and putting the data flow graph into the FPGA as is, fully pipelining it so that I can achieve a clock frequency of the data rate. Basically, I'm clocking this circuit once for every wave of data that is coming in, which is also the minimal clock frequency that you can use in order to evaluate this particular circuit. And use very small arithmetic units that reduce the size of the circuit, and basically create a pipeline that is maybe 200 clock cycles deep. So for one data item to go through this pipeline, it takes about maybe 200 clock cycles. But then every following clock cycle, you get the data item out. So you get very high throughputs, and therefore very high performance if you look at the time it takes to encrypt, let's say, 1 megabyte of data. Looking at the numbers here, We have power delay as a function of capacitance frequency, voltage, and delay. Very straightforward. We reduce the clock frequency to a minimum. We reduce the delay by having the architecture that pipelines the whole thing and creates very high data rates. And we increase the capacitance because we're using now an FPGA instead of a very small microprocessor. And for this particular application, we saw that there is actually up to an order of magnitude gain in doing that. And the question is really to how many applications this can be extended and done. But this is just to show that there is a huge potential here to actually reduce the power. So if we look at the global picture here, putting everything together, we have applications where the kernel loop or the loop that is being executed most of the time is bound by CPU performance. And we have such loops that are bound by memory performance, or either memory bandwidth or memory latency. So we can split both cases into bandwidth problems and latency problems. And I've shown you a couple of approaches for each one of these cases on how you can obtain competitive or better performance on FPGAs if you compare it to microprocessors. So now we get to the second part of the talk. We've seen that we have the potential to create high performance, low power implementations of applications. Now, how do we program these? Unless it becomes significantly easier to access this performance, it is really not very useful because it takes significant effort to implement each one of these that I've shown before. And I'll show a couple of examples on how to simplify the programming. Other issues are also maintenance and portability of such codes, but that's not something that I'm going to get into here in this talk. So before I get started with the programming, just to show the magnitude of the problem, we have here VLSI synthesis and what analysts think that is going on there. If we look at that, we see that productivity of the average engineer in designing circuits for VLSI grows at 21% a year, while the complexity of the actual design grows at 58%. And that problem is significant in VLSI design, and there is a similar problem going on when you want to program FPGAs, because at the end of the day, really what you're doing is designing circuits. What the second slide here shows is that actually the problem is not as similar as it looks first. While circuits for VLSI are hard circuits, basically circuits that you design once and you have to make sure that they work forever. They have to work for all cases. They have to work for variable temperatures and whatever people want to use them at. The FPGA circuit is a software issue, and you can really ship a product over the internet and then ship a bug fix or ship a patch, just as you do for software. And if you find another bug, you simply fix it by shipping another circuit. So you don't need to go through as rigorous verification and testing as you do in the VLSI side. Programming FPGAs is more similar to actually programming microprocessors, where you write some code, you push a button, you can download it within 100 milliseconds, and you just go through the loop of programming trial and error to figure out what it is that you want to write. You can have various libraries that people can write and share, which is very hard in the VLSI world because there is so much more effort going into designing all these modules. So if there is a lot of effort, it's also very hard to get it for free, while if it's very simple to build modules or little programs, it's also much easier to share them and basically have many more of them out there. Another issue is retiming. If you want to, for example, have a circuit and you want to change the number of registers in this circuit, for VLSI, you really have all the options out there. You can put the registers wherever you want. Versus in an FPGA, you really have this fixed architecture where the locations of the registers are fixed, And you have these registers there if you want or not, so you could as well use them in just the place where they are. So the problem is slightly transformed, just to show that there are significantly different problems out there when dealing with programming FPGAs as opposed to VLSI. Now, lastly, I have here 3 points on what the implications could be on changing the circuit every 100 milliseconds. And one that I already mentioned is that there is no verification, or there is no need for verification, because you can simply try it out. If it doesn't work, you'll fix it at some point. Nobody has ever verified Unix, I think, and nobody has ever tried to verify C libraries. But you simply assume that they're working until you find a bug, you send in a bug report, they'll fix it, they'll ship you a working version, and you're done with it. So that's a little bit of a different environment that you really have for designing these circuits. Now, when you program FPGAs, what you have to do, basically, you have the flexibility on the algorithm level, the architecture level, and the bit level. And dealing with this flexibility on all 3 levels is what we would try to do inside the programming environment that we have. So now the task of the programmer, when you look at it, at what all the things are that you have to do when implementing or programming such an FPGA, you have to pick an algorithm like when you work on a microprocessor. But then you also have to pick an architecture or a structure that is going to evaluate this particular algorithm. And you can also pick the arithmetic or the number representation that you're using. Where a microprocessor has integers and floating point numbers, because this was a minimal set of number representations that people agreed on that they need. We are not restricted to these in an FPGA. You could have any type of number representation. You can have any number of bits for any variable, which is at first a little bit difficult to grasp, because you're used to having 16-bit integers, and we got used to thinking, well, we'll just pick whatever bit we need, and then we just have to go with it, because that's what my data path in my microprocessor is. There is no need to do that. You can actually specify any bit width and just have a compiler figure out how to build your architecture with the different bits that you have in your data representation. So now, if we look at what I'm trying to do here, we look at what C does to a microprocessor. You have assembly instructions or opcodes, and here comes C and says, I'm providing a higher level interface, a language that has the same types that my architecture supports, easy mapping from the language down to assembly, but I'm not going to keep, for example, the number of registers in my language. I'm not going to keep the actual limitations of my architecture that I have. I'm going to let the compiler do register allocation and scheduling, which is something that I can easily do in a compiler and that is tedious to do for the programmer. But I'm going to let the programmer decide if a variable is going to be an integer or a floating point number, because that's something that the programmer can easily figure out. It's not a too hard decision, and it's very hard for a compiler to actually make the optimal decision in terms of which data type should be used for a particular operation. Doing the same thing for FPGAs, now we don't have an instruction set. Instead of an instruction set, we have module generators. So basically, we have a huge number of instructions. Any module that we possibly could get our hands on, we gathered into our little database. That's our instruction set. And we're trying to map an application down to this particular instruction set that is limited by the amount of modules that I have in my module generation environment. Now, in order to map that down to the modules, I want to use the same idea, basically having types and operators on these types. So you could imagine number representations being the types that are supported, where the width is part of the number representation. And the operations on these number representations can be mapped automatically by a compiler to the modules that you have in your module generation environment. Now, I'm working at this one particular compiler that is going down to FPGAs. And the general concept here is that we're splitting up the design space of architectures into application domains, where each application domain basically corresponds to a particular way of doing computation, a particular architecture. And when I say architecture, I mean something like a microprocessor, which is a specific architecture to implement a particular function, or the stream architecture that I just showed before, which is a slightly different way of computing. So once we know that we are targeting a stream architecture, we can write a compiler that targets this particular architecture, which is a stream architecture, and knows how to do the equivalent of register allocation or scheduling for this particular architecture. So you have an infrastructure below that is basically the module generation environment, and you can target that module generation environment with a set of different compilers that are each specialized to a particular architecture. They know this one architecture and they know how to map to that architecture, but they have less a concept of which architecture you should be choosing. So choosing a particular type of architecture is left to the programmer, and mapping the algorithm down to that particular architecture is being shared between the programmer and the compiler. Looking at the levels of abstraction, if we compare microprocessors, FPGAs, and ASICs here, we have in VLSI synthesis, we have software that maps all the way down from an algorithm down to the gate level, has ultimate flexibility, and there are levels of abstraction that the people have figured out that they want to go for, and have different tools to do that. For FPGAs, what I'm suggesting here is to have the module generation and the domain-specific compilers on top of that that map down to these particular module generation environments. Here is the little bit more detail on the C++ class structure that the compiler is using, just to show the mapping between the ideas before and C++ is a language to implement these kind of ideas. And there is really a very nice match between the classes provided in C++ and the idea of modules and mapping down to these modules, where you can encapsulate hardware objects inside a C++ class and map down to that. Same way you can encapsulate an architecture as a C++ class and map the actual modules into that class by just overloading the operators of the different representations that we have. So I have a couple examples here. Before we go into the examples, the main question that arises is, you have the architecture and you have a program. How do you define which pieces of the program map onto which pieces of your architecture? How do you map your algorithm down to that particular architecture once you know what the architecture is? And the way this is done at the current moment is for the stream architecture, you have different types of variables or different kinds of variables. You can see in this structure there are 4 streams coming in 0 to in 3. And you have 4 streams coming out, out 0 to out 3. And you have other variables that are intermediate variables that just connect the nodes inside of your data flow graph that we want to put down into the FPGA. And then there are these little worms that I have between the bubbles, which are denoting FIFOs. And these are really part of the scheduling, where we want to ensure that all data items arrive at the right time to their arithmetic unit. So you have, let's say, an add that needs 2 operands. You want the 2 operands to get to the add at the right time. So here's one example. You can see there is a hardware integer that is the type of the variable in. And I declare that to be an input or a stream into that architecture. I can also tell how many bits I want that to be. And I can declare various other types like that, and then just simply write a program that uses regular C++ syntax to describe what it is that I want to compute. And I've solved the problems that are really hard to solve for the compiler, which is how to map the variables onto the particular features of my architecture. And I let the compiler do things like scheduling and building of the data flow graph, shifting between different sizes of operations, putting everything together the way that makes actual sense, and get me the resulting circuit. Another example here, a little bit larger, is the ID encryption, where I started in the beginning by writing many pages of RTL level code to create the ID encryption in the beginning. Here I can just write a couple lines of code that give me the full encryption, and I didn't even have to write this because the definition of the ID encryption algorithm is in C, and you just get it down from the web. And all you need to do is to change the types to basically set which variables have which functionality in your architecture, and it compiles down into that architecture just by compiling it with a GNU C++ compiler. Another example here that shows a compound arithmetic unit. We can basically build an arithmetic unit that is much more powerful than the general add and subtract. For example, we can have a rotate primitive that takes x and y and an angle and rotates x and y. And we can build a 3D motion circuit where I stream in 3 inputs. The 3 inputs are x, y, and z of a point in 3-dimensional space. And these couple of operations here simply move and rotate this point to another position, and I get another x, y, and z out at the bottom of this whole thing. The rotate primitive here is simply just a primitive that I have in my module generation environment. So it's one of my instructions, and I don't really have to bother with how this is implemented or why this is actually rotating a point, all these tricky issues. So now, a question that arises is, what if there is a loop with a dependency? How do I deal with the actual problem that I have a dependency and a loop around it? And there is a straightforward example here, a Fibonacci series, where you really need the previous 2 values in order to get the next value. And the delay of your addition is really what limits your performance. And the way to do that is, for example, to choose a number representation where this add can be done very quickly. So you could transform x and y, x into a redundant representation and use redundant arithmetic to speed up the actual computation. And with this trick, you can basically try to make up for the 5 times slower adder that you have in an FPGA as compared to a microprocessor. So the microprocessor will just have the fastest adder available and spin through it, versus here I would have to use a more redundant representation, use more bits to represent my number, but then have a much faster execution. So that's one way of dealing with this. And the conclusion is basically that our compilers have to now become experts in arithmetic in order to be able to do these kind of things. So what does that mean? Well, what are all the possibilities, all the tricks, bells, and whistles that we want to pull on this particular issue? And here just a couple that I could think of at the top of my head, which is to look at the number representation. We can look at the precision and range that we want to have. We can look at the arithmetic style, of course, where we have sequential, parallel, pipeline, combinational, various kinds. And we can look at larger functions, like I showed before, the rotation primitive. You can implement the whole thing and just map down to a very efficient little hardware structure that implements a larger function. And also, maybe less significant, but also interesting for these type of problems, you can take a fresh look at rounding and overflow modes, and maybe find more appropriate rounding and overflow modes for particular applications. Now, looking at the details here, we have, let's say in the previous case, we had just hardware integers, but we could as well have a hardware fix variable. We could have a hardware log variable or type. We could have a redundant variable type. We could have residue numbers. And these are all fairly standard arithmetic methods that people use in order to design VLSI chips. And we can basically move these type of methods into the compiler. The compiler can understand how to deal with these representations. And you simply let the programmer understand what happens if he uses this particular number representation without the need to actually understand how I add two residue numbers or how I multiply two redundant numbers or things like that. A second point was precision and range optimization. We want to find the optimal number of bits that we really need in order to represent a particular data value. And this is turned out to be quite a challenge. There are lots of different things that need to be considered when trying to limit the number of bits. The advantages of why we're trying to do this are basically we could convert floating point to fixed point code, which has obvious advantages in execution speed. We reduce memory bandwidth because we are now trying to get less data from the memory. We're just getting the data that we actually need. We minimize the area on the FPGA and reduce the latency for these particular applications. And we can therefore also decrease maybe power consumption. So these are all ways to try to optimize an inefficient implementation on the FPGA. And once you can optimize more than you lose with the FPGA, you actually have a better implementation than you have on the microprocessor. So the direction that we are currently looking at is really to combine interval arithmetic and something called automatic differentiation. But that's also beyond the time that I have here, so I'm not going to get too much into that. Arithmetic styles are straightforward. You can pipeline, you can parallelize, you can build a combinational circuit. Fairly straightforward stuff, really. Really, this is the one that you don't want to use because there is a lot of control overhead. But all the others are fair game and can be used to optimize what you're doing. Now, I talked a little bit about compound arithmetic. If you want to implement a larger function, one of the problems, I said, we can have any bit width. But let's say you want to compute a sign of a number. You need to be able to generate a 17-bit sign generator. And there is a significant problem. How do you create the parameterization? How do you generate a sign generator for a particular bit width? And for this particular architecture that I show up here, they basically figured out how to do that. And there is a nice mathematical formula that you just plug in, and you get how many bits you need in your table and how many bits you need for your multiply add, and you can basically evaluate your function, whatever the function is, to a particular precision. Now, to slowly wrap up here, I have a couple thoughts on syntax and semantics that they're just hand-waving arguments, really, but just to show what the ideas are here. There are basically two objectives that you can have. Either you want the language to be easy to use, or you want the language to be easy to learn. If it's easy to use, you assume that the person is already an expert in using this language, and this is really the most perfect language to express a particular problem in. And the problem is, it's hard to persuade people to actually learn your language. The other approach is you go for the most common language that everybody already knows, and you try to squeeze your problem that doesn't fit that language somehow onto that, and see if you can map from that language that everybody speaks down to whatever you want to do. And in my opinion, which is a little bit biased here, it seems like the C++ approach that I'm going is really the easy to learn one, where most people already know C or C++, and we're trying to squeeze whatever we want to do onto that language. Where maybe a better approach would be to use other languages, maybe functional languages, or languages that encapsulate more of the structure of what you actually want to do. The problem there seems to be, or most people that advocate that have a big struggle in convincing the rest of the world that this is really a good way to do things and that you really should sit down and learn this new way of programming and structuring your problems. On the semantics side, we really need to map from the semantics that you have in designing this architecture down to a particular language. And what you currently do if you use a hardware description language, you use languages that were really meant for simulation and were kind of cut and squeezed and pushed into a little box in order to be synthesizable and to get the circuit out. Versus what we really need is to get back on the semantics, also to look at ease of learning them or ease of use. So now, going beyond that work, what I've assumed is that we will take a couple of architectures and try to map to these architectures. But we really have the flexibility on the architecture level. And the main open question that I see here is really, given a particular problem, how many architectures are there to evaluate this? How do we look at the design space? We don't even have a clue of what the number of possible architectures is that we could possibly map that to. What we have is we have point solutions. We have whole fields that go towards solving problems with a particular architecture. Let's say like neural networks. There's a whole field out there, lots of people looking at how to solve things with neural networks. But if you're not in that field, you're probably not going to consider using it. And there's also no way to quantify how a neural network as an architecture compares to now a systolic array or a microprocessor or a stream architecture, or any other way to do these kind of things. So I see that really as the main challenge of programming FPGAs, to somehow try to understand what the possibilities are, what is out there in terms of architectures, what is the design space, how can we parameterize such a design space, and look at how to compute on FPGAs. So to summarize, I've showed that there is a potential to speed up applications up to 100 times. Shown that there is more than one application where we can actually achieve a speed up. The main problem are the two little words "up to," and the question is, you can get the speed up to 100, but how can you consistently get the speed up for a wide range of applications? How can you use these kind of things? I've shown one little example of an architecture where you have a good potential to do these kind of things. Shown the use of domain-specific arithmetic, how you can map or use the flexibility on the bit level on FPGA to actually gain a benefit or gain an advantage over a microprocessor. And I've shown the example of the stream compiler. Now this little circle down at the end of this slide really shows why I'm having so much fun doing this kind of thing. And the nice thing about it is that you can work on the architecture of what you're trying to do and on the compiler and do the cycle of doing this on a daily basis as opposed to on a yearly basis, as is done for microprocessors, where people worked on the architecture and then the compiler guys take over and they figure out how they compile to some other features, and then they're being put into the microprocessor. And each spin around this loop between compiler people and architecture people really takes about a year or two at least until they get together and can do something. Whereas here you have a very tight loop and you can actually move fairly quickly once you know what you're doing. Thank you.
We've got time for questions.
As I understand it, your FPGAs were originally created for prototyping and rapid development, where you're not using them for extended duration tasks. How, if at all, would you prefer FPGAs to be designed to suit better your needs in using them for extended computing?
It's really a hard question. How would I change FPGAs if I would want them to be more suitable for computing? That question is really slightly orthogonal to what I'm trying to do, and there are lots of people looking into that. The main problem with that is that you would have to understand what it is that you want to create. So it's kind of a chicken and egg problem, and I don't understand yet all the possibilities of what it is that I want to generate. That's why I think it's a little bit too early to start thinking about what the optimal architecture for the FPGA is. I think the way it is now, it is good enough for us to reason about what we want to generate on these chips. Once we have a better understanding of what it is that we can map down onto FPGAs, it will also be easier to answer that question. So I think my answer is I don't know. Yeah.
There's a company called Siloxica, whose technology is based on work done at Oxford University. And they have a language based on C, and the claim they're making is that C programmers come up to speed very quickly on the language and are programming some very impressive applications. And if you were at FCCM over the last 3 days, you would have seen very impressive demonstrations of what the C programmers could do in a very short amount, relatively short amount of time. Are you aware of Siloxica's technology, and if so, do you have any comments on it?
Yeah,
in particular, have they solved the programming problem?
They have certainly advanced the state of the art in programming FPGAs, and they are basically providing a product, something that is feasible today with today's technology and today's understanding of these architectures. The difference between what I'm trying to do and what they're doing is that they're selling a product that is currently targeted to what people want to do on FPGAs, which is getting people up to speed quickly to design circuits much faster. There is very little information on the actual architecture that is being compiled to, which provides some difficulty for people to get started. Also, there is not even close to the flexibility that I was talking about here in terms of arithmetic and in terms of various other things that I showed in this talk, which would take too long. So the difference between the two projects is really that one is more market-oriented and the other one is more research-oriented, where I hope that what I'm doing here will be feasible, or somebody would pay money for it, maybe in the 10-year time frame. So, yeah.
When you trying to come up with a speed up figure like that, how do you determine which process to compare the FPGA to?
Well, that's a good question. I mean, basically, you pick one and then show the number. Microprocessors of a given technology with a given clock frequency don't vary that much in performance. You don't have 5 times different performance if you run a program on an Alpha versus a Pentium. It's 20, 30%, 50% different. So that's why this number has just really 1 or 2 significant digits. Because I don't care if it's 99.5 or 101.5. It's just to show the ballpark that there is a potential for order of magnitude improvement. The actual number at this point is not meaningful exactly for that reason. Yeah.
Your algorithms specifically take into account the large performance that you get every time you need to perform. You mentioned one algorithm where you said you could divide things up into smaller chunks. But you also programming. How do you address it?
The idea is that you have to justify changing the circuit on the FPGA by running the circuit about 10 times longer than it takes to actually change the configuration. So that's usually the way it is done. That's why people like to implement applications with a lot of data, because you simply gain the flexibility in time where you can process 1 megabyte of data. And that can take a while, can take long enough to justify reconfiguring the FPGA and doing it again. So that's why I didn't show too much about the first couple applications that I had, which deal with applications that have a lot of data, because this is a rather trivial problem. Because you simply you process enough data to justify the reconfiguration. So that's why the applications that I showed are slightly tougher problems, where you actually have tighter loops, or you have the memory in there, or you have other types of problems that are slightly harder to address.
Your streams was motivational.
Yes. So the stream compiler basically that's what it does. It streams the data through lets the data being streamed through the FPGA and to justify the reconfiguration by having enough data to process.
Oskar, one of the ways you get performance increase in this sort of model is to take advantage of inherent parallelism. You're specifying your algorithms, however, in terms of C++, which is, if anything, a sequential language. How do you discover the parallelism? How do you map things out? Or are you simply really just recreating the C++ program as a data flow program in the FPGA?
It is really the recreation of the program. So you take the data flow graph of whatever it is that you have, and you just put it into the FPGA as is. And that makes it very simple to fully pipeline. And it makes it also very simple to just handle the control of that. So there is no control overhead. There is no power or area or time wasted on controlling that circuit. There essentially is no control because data only streams through, which is another advantage of this architecture of microprocessors that spend a lot of time decoding and looking at instructions and piping them through.
True, but many algorithms would perhaps decompose into multiple pipelines which operate independently. And you could get even additional performance if you were able to discover that. Is this something which you're going to look at some point?
Definitely, yes.
How do you handle loops?
Well, loops, the way it is handled now, are being unrolled. So you have a loop and you unroll the loop in order to create the full data flow graph. So that's one way of handling loops if you know how. So basically there are different types of loops. You have loops that loop through an array, which is basically going through the array and streaming that array into a stream architecture. There are other types of loops where you do something 5 times, which can be easily unrolled. And then there are again other types of loops where you have a dependency between the loops and you have to figure out when to stop looping. Basically, you have a condition on the end of the loop. And that is what I was talking about on the one slide with looking at loops, which is where you need the feedback inside your data flow graph. And you have to optimize the critical path through this loop in order to get your performance up. And this is where you use the number representations to shorten that critical path.
No, but then how do you achieve pipeline in that case? You just wait for the entire task to flow beyond that loop before you can get the next task in?
Pipelining is implicit in the architecture. You have, for example, a multiplier that is already pipelined. Like I said, the registers are fixed in the FPGA. You can't move them. You can as well use them, right? After you go through a lookup table or some piece of logic, you can as well go into a register because it's already there. Not using it is not going to help you much. So you know already where the registers are, and there is really no big question about where to put them. So pipelining is implicit. Yes?
It would seem that this technology has tremendous potential for evolutionary programming, adaptive systems. Is that caught on yet? Are we in that age?
Yes. John Koza is doing experiments for a couple of years already, evolving all kinds of circuits or helping evolution or doing these kind of things. So yes, there are a couple papers out. They're still in a very initial stage and lots of problems associated with them, but we've started looking.
What did you think of the ideas that Mr. Denick was presenting? Basically, one way to implement large, complicated systems would be to swap in and swap out to a FPGA engine, a particular architecture for doing a particular thing.
Well, Nick has a little bit more radical ideas. To tell the truth, I'm not really sure how I would do that. But I'm always interested to see how this would work. So.
Any other questions? Okay, thanks very much.